Okay, so today's second meeting, and it is about, we will discuss what is the quantum bit as a base part of memory in quantum computing. And we'll discuss what we can do with quantum bit. It is unitary transformations and measurements. And there will be one example of streaming algorithm with 1-qubit that show us that quantum algorithm can be more effective than classical ones, and it will use much less memory than in classical algorithm. Okay, let's start. So firstly, let's discuss step by step. Let's get some formalization of classical bit and then move to quantum bit. So the deterministic bit or regular bit has two states. It is 0 or 1. And we will show it on Cartesian plane. So the OX axis will be for 0 value, and OY axis will be for 1 value. And we will use 2 points as two different states of bit, one on the with coordinates 0, 1, and second one with coordinates 1, 0. And because it is some vector, we will use notation that is typically used in quantum physics, that's called Dirac notation. And this unit vector for 0 axis will that is 1, 0. We denote it as this one, this like line, 0, and some kind of bracket. And for OX unit vector, it will be it is vector 0, 1. We'll denote it like this, 1. This line, then something, then this kind of angle means that it is a column vector. If we want, and between and this one, it is just name of vector. It is 1 vector and 0 vector. And if we want to write line vector, row vector, then we put angle, name, and then line. So it is like different opposite direction. So what we can do with deterministic bit, we just can change its state from 0 to 1. Yeah, it can be like this vector or this vector. And so it is, and this is only the way how we can manipulate it. And if we want to read value from this bit, we just get this value 0 or 1. So it is just for using this new formalization because it will be useful for random bit and quantum bit. Okay. So deterministic bit have 0 or 1 value. What with the randomized bit or random bit, so it is like a bit that can be in 0 state with probability P0 and 1 state with probability P1. So assume that we have some randomized algorithm that change this value depends on some randomized mechanism. And so on each step of your algorithm, you have this probability distribution for two values, 0 and 1. What we know that sum of probabilities is 1 and probability from 0 to 1. And so we can represent it also like, so it is column vector, and we can represent it as a sum of unit column vectors, 0 and 1 times these probabilities. So we will write it in this way. In that case, we can say that each possible state of your random bit, it is just some point on this segment that connect points 0, 1 and 1, 0. What you can do, just what algorithm do if it change the probability distribution, it means that it moves this point on this segment to one position or another. Okay, this changing of state, how we can represent it? We can represent it like a multiplication to stochastic matrix. Do you know what's stochastic matrix?
Yeah.
Okay, so just simple property that sum of elements in line is 1. For our random bit, what is the property of this matrix is this 2 times 2 matrix, such that Mij element, it is the probability that we have been in state I and move to state J. So how we can compute it? New probability distribution. It is just a probability that we was in state 0 times probability of moving from state 0 to 0 plus probability that we are in state 1 times probability of moving from state 1 to 0. And this is total probability of being on the state 0 after this manipulation. And the similar to one step, yes. And the similar to for state 1. So it is just multiplication of p row vector to m times p row vector. Okay, it is what we can. What is the one step of algorithm and how to read to obtain some value from this bit? It is just you obtain 0 or you obtain 1, but with some probability. You obtain 0 with probability p0 and 1 with probability p1. It is like if you want to output the value of this bit, you output 0 or 1 with these probabilities. Okay, quantum bit is something similar to this random bit, but with small modifications. Okay, quantum bit, it is also a row vector, and also it have 2 coordinates. It is A0 and A1. We call them amplitude, not probability like here in randomized or random bit or randomized bit, but we call it here amplitude. That's why it's A0, A1. And formally, it is complex numbers of amplitude, such that sum of the square of the models is 1. Sorry?
Yeah, no, yes.
Okay. Okay, why we get this formalization of state of quantum bit? Because one of the main models of quantum bit, it is like some, so it is some sphere that is model for electron or some I forgot how in English, ion, I think, IOAN, ion. this, no, okay, let's be electron that have, let me check how to English this works, sorry, forgot it.
It froze.
Okay, it is like, 1 second.
Ion.
It's ion, yes, ION means. So, and this ion have so-called spin. It is just direction. Around this direction, it's rotating or spinning around this direction, and it can be represented as point in three-dimensional space, so by 3 real numbers, or by 2 complex numbers. There is a mapping from 3 real numbers to 2 complex numbers that calls block sphere, and these 2 complex numbers is much more easier to use in quantum algorithm. But in our lectures, we will use only real numbers as amplitudes, not complex numbers. And if it is real numbers, then we can say that state of qubit, it is just some point on unit circle.
Yeah.
Because the square root is 1. Very good. And what is the possible modification? It is just rotation on or reflection on this sphere. Sorry, not sphere, but circle, unit circle. And it can be represented by multiplication to unitary matrix. So unitary matrix, that means that U times U star is 1, where U star is transposed conjugated matrix for this matrix U. Okay. Any questions? Is it clear now? This point. Okay, can you hear me? I cannot hear you. Is it clear? Sorry, I cannot hear you. Okay, any questions?
So.
Is it clear?
Yeah, this part I actually understand it because I've read it in some papers about like fused logic and quantum computer like a few years ago.
Okay, good. So next, how we can read information from quantum bit? It is just we obtain 0 or 1 with probability A0 square or A1 square. It is like from random bit, but it is not the probability that is coordinates of our point bar square. Okay, this is the basic things. Let's try to solve one problem, and I think it's enough for today. So we have such problem. We have input stream, and we have promise. The D is some parameter of our problem. It is known. Known integer, and we have promise that the number of it is binary string and number of ones in this binary string is always v times some power of 2 to the d. V times 2 to the d. The question is, what is the v mod 2? So is v odd or even? How you solve it firstly not in quantum way, but in some classical way? How you solve it? How you can construct streaming algorithm that?
I mean, I think I didn't understood the question because, like, if d is not zero, the number is going to be even always.
The question is this v times.
Oh,
So the number of ones is v times 2 to the d, and the question is is v odd or even?
Oh, I see. Okay. So we have a number that is our input string is b, or is v times 2d 2d. Yeah, okay. Our input string is the binary form of b elevated v times 2 elevated d. Yeah. Okay, so I will take the this plus 1 position of this input string, and it's just check if it's 0 or 1. If it's 0, the number v is odd, is even. If it's 1, is odd.
Okay, and
the justification of this is that if I have an entire number times 2 elevated to d, I have like the first d strings, like the first d numbers on the binary representation are fixed to be 0, and the rest numbers will be the binary representation of b. So if I took the d plus 1 position, I will have actually the first position, the least significant bit on v, and that least significant bit is 0 if b is pair, if even, and 1 if v is odd.
okay, let's look to some example. So d, for example, 2. Okay, so like this, you read first d plus 1, yeah, bits.
You actually only have to fix 1 bit, but it's like it got to be reversed. Because like for example, if you have v equal 3 and d equal 2, you will have initially just 3 that is 11 in binary 1 1, and if you multiply 3 times 4, that's 12, that is 11, is 1 1 0 0. Yeah, so multiplying any number by 4, it's just adding 2 zeros at the end, appending 2 zeros at the end. So if you know that, you ignore the first the characters of the input stream. I said the first, but it's actually the last two characters, and the first one remaining, the last one remaining, is the least significant bit of the input stream b, of the number representation of b, and that least significant bit, it gives you the parity. It gives you this odd or even.
Okay, how many bits do you use in that case? For
I will be needing only d plus 1, actually.
Okay, good, yes. So using d plus 1 bits, it is enough here. And okay, and in fact, it is known that for any classical algorithms, it means randomized or deterministic, D+1 is required memory, because if you use less memory, then there is input where we can, it can be mistake for algorithm. But let's think how to compute this, solve this problem using quantum algorithm. So I mean, if we have only one qubit, and how we can check this V is odd or even. Do you have any idea?
No,
So what
I
we
don't
can
think
do,
so.
we have this unit circle, and the main question is, after measurement, is it on the 0 state or 1 state? Yeah, on the OX axis or Y axis. And what we can do, we can rotate point on this circle. Oh, yes, circle.
Yeah, I don't think I can come up with a solution right now.
Okay, let me tell you how to do it. What we do, so for example, this input, we consider this circle and split quarter of circle to 2 to the d parts. So it means that we consider one angle alpha, that is p over 2 times 2 to the d. Yeah. And what we do, when we meet 1, then we just rotate to angle alpha. If we meet 1 again, if we meet 0, we do nothing, because we just count once. Okay, what do you think? What happens when we read 2 to the d 1 times? So this block of ones of size 2 to the d.
What happens if we read?
Well, what happens if we read block of ones such that the size of these blocks is 2 to the d? Of this size.
Okay. Well, the angle will be p over 2.
Yes, angle will be p over 2. Yeah. And after next 2 to the d ones, it will be p, then next 2 to 3p over 2, then 0, and so on. You can see that each block of 2 to the d, it's the point will be on the one of these two positions. And if v mod 2 is 0, then it will be 0 or pi or 0. Yeah, these two positions. And if the v mod 2 is 1, then position is pi over 2 and 3 pi over 2, or this or this. Is clear? Okay. Here,
I mean, I will give it a try, but because it's not super clear the why. But okay, yeah.
So I mean, one block of ones of size 2 to the d. With one blocks, we move to this position. So second block, we will
with the
move
second
to this.
block, we
Third
move
here,
to,
fourth, fifth, and so on.
Block.
Here will be odd number of blocks, and here will be for even number of blocks.
even number of blocks, yeah.
Okay, here coordinate, the state of qubit is 1, 0. Here minus 1, 0.
1.
Yeah. Here 0, 1. And
Yeah.
here 0, minus 1. Yeah.
1.
Do you see?
Yeah.
Okay,
So
good.
it's a square model of, yeah, I got it.
So, and if we measure our qubit after reading all the input, we measure it, and if it is in this state or this state 0 or pi, then the square of state 0 is the square of this amplitude is 1, and square of this amplitude is 0. It means that we obtain 0 state with probability 1. Yeah.
Yeah.
And if it is in
And 0 state is pi.
this state or this state, the square of amplitude for state 1 is 1, and square of amplitude for state 0 is 0. And we obtain 1 with probability 1.
Yeah. Okay. Yeah. I kind of got the idea, but the proof that each d blocks of one's font do change the parity of the number v is not quite clear to me. I will try to give it a proof like with pen and paper later.
Okay.
But again, the idea of the algorithm, I do understand it.
So, okay. So, but what, so let me tell you maybe another explanation once more, maybe it will be easier. It is like for classical algorithm, what we can do, we can count, so we can use two variables, some, don't know, z and c, where c is counting number of ones, counting until it is if c is 2 to the d, yeah, equals. Then what we do, we firstly assign 0 again to counting for next block, and then put to the z plus 1 mod 4, like this. So it is like counting what is the so counting the number of blocks by modulo 4. In fact, for deterministic algorithm, it is enough for counting by modulo 2 and returning just z. It is z will be z is v mod 2. Yeah. In that case.
Yeah.
But in quantum algorithm, it is like we counting it is mod 4, and v mod z mod 2, it is the same as v mod 2.
Yeah.
Yeah. And here z, it is like this place is z is 0, here z is 1, here z is 2, and here z is 3.
Yeah.
Yeah. And we can recognize what is z is odd or even, because for these 2 points we have 0, 1 or minus 0, or sorry, 1, 0 and minus 1, 0 coordinates, and here 0, 1 and 0, minus 1. And by definition, okay, maybe I have this slide. By definition, when we stop if we are on one of these states, we measure our qubit and obtain. So it is like A0 and A1, two coordinates. Obtain result 0 with probability A0 square. Yeah. But for and this is for 0 result. And for 1 result, it is A1 square. Yeah, and for example, if we are here, yes, on this state where 0 is 0, z is 0, it is 1, 0. It means that probability of 0 is 1, probability of 1 is 0. We obtain 0 result. And here, for example, also we obtain 0 result because it is -1 square, it is also 1. And so 0 square is 0. Here also 0 result. And here and here we obtain 1 result. And by this result 0 or 1, we can say that what is the answer? Is it 0 or 1? Does it become a little bit more clear or not?
Yeah.
Okay. It is all what I want to tell for today. If you have question, please give me. If not, then for next lesson we will move to some basis operations, like standard operation that we can do with qubit. And so discuss some other applications.
Okay, then see you next lesson.
Sorry?
Yeah, okay. I don't have any remaining question about this. So yeah. Okay, see you next lesson.
Okay, yes, see you next lesson.